Up next, we'll hear from Ali Farzbad with SeebeckCell Technologies. Ali earned our Early Bird Award and was voted most likely to take a meeting at 6 a.m. with Caroline.
Hi, everyone. My name is Ali Farzbad, and I'm CEO co-founder of SeebeckCell Technologies. Our goal is to harness waste heat through our clean technology. Whether you're using or generating electricity, on average, you're losing 60% of that through heat. Petroleum industry has the biggest share, and that brings up the waste recovery market around $55 billion. We all know energy demand is increasing, and it is critical to look at different methods such as recovery for supplying that demand. Ironically, in the places that they create energy commodities, there is a huge and significant demand for electrical power due to ESG and electrification. That's where we come in. We harvest that waste heat to convert it to electricity, and we store it in the same module using our clean technology. The main component of our technology is ionic liquids, which are applicable to different temperature ranges, and they are synthesizable, meaning they can easily get scaled up and much more cost-effective compared to their semiconductor counterparts. This platform technology has been developed by me 3 years ago in my PhD studies. University of Texas at Arlington owned the patent, and we have the exclusive right to this patent. This patent covers the power generation in low power, medium power, and high power schemes. Obviously, looking at different verticals to commercialize this technology, we did our customer discovery, and we realized that a passive power generator, which utilizes the waste heat in industrial setting and provide power for IoTs, is the best featured market. Currently, majority of the sensors are using battery, and they require to get changed every 3 to 6 months. Set aside the cost of that battery, there is 15 minutes of man hour for changing each battery. If you don't believe that, try next time when you are changing a battery of your remote. What we do, we retrofit our devices around that waste heat around the source, and we harvest that waste heat that you're already using and provide it for recharging your batteries or directly to your sensor. That enable a faster sensor rate if you need to, and enable new capabilities in subsea applications. Our business model is direct sale to oil and gas and suppliers at the beginning. And while we are increasing our share in that market, we want to utilize our high efficiency in low temperature waste heat recovery and enter an emerging market, which is waste heat recovery from data centers and blockchain. While we are doing that, we already partnered up with UTA, University of Texas at Arlington, to do federal grants and contracts with defense agencies. With reaching our technological milestone, we'll be able to license our technology to battery electric vehicle manufacturer for harvesting the heat base coming from their battery. Our competitive landscape in terms of non-moving waste heat recovery market, we beat all the other competitors in regard to cost because we are using a synthesizable material compared to a mining semiconductor, which has a very high carbon intensity for production. And also because we replace that solid state with a liquid material, we increase our power per weight ratio significantly, making us more appealing for transportation and space applications. Our team is including me, Dr. Prunoruz, who has extensive experience and knowledge in this field. And we are also having Jack, who is a serial entrepreneur and has experience in manufacturing companies. We are benefiting from advisors ranging from former vice presidents of BP to Los Alamos Scientist Lab and faculty fellow at Aerospace Research Lab. Right now, we are at TRL4. We are raising our seed round to build our pilot product and have it deployed with the help of IoT companies. And we're anticipating to have our seed round by December 2022 and having our product launched by August 2023. We believe and predicted that we will be break-even 4 years after our completion of seed round. With that, I'll ask seed investors and anyone who has expertise in IoT operation, come join our company and let's power the next generation of IoTs.
Thank you, Ali. We'll now open it up for questions. We have our first from Raj. Isn't Everactive your competitor as well, or do you see them differently?
We see them differently because our operation is mainly harvesting waste heat, which is you're already losing. So it has a carbon negative basically generation built into it, which we believe that later on can come into other calculations in terms of offset cycle analysis.
Next question from Vincent. How much will your cell weigh?
Sorry, I didn't get the question, if you can.
How much will your cell weigh?
Oh, so the performance of the cell is basically rely on two main components. One is the area of the cell, which we applied on. I mean, basically the heat source is being applied on, and then the temperature difference of it, right? So depends on the efficiency required and the power required. We can design that to provide the power requirement for each sensor. So right now, we believe that for 1 watt sensor, it comes around 400 grams. I mean, right now we are using 3D printing material, and that's just estimation. But that's something that we want to investigate as we do life cycle studies in pilot run.
Thank you for the question. Another one from Jim. How do you convert the waste heat to electricity?
So this is a totally different paradigm regarding the semiconductor. Basically, we have this ionic liquid which we tweak with adding nanoparticles into it. We create a nano fluid, and when this heat goes through these cells, basically this ionic liquid create a charge difference by having a different mobility because of that heat going through it. So we harvest them through either adding redox couple or creating a surface enhancement at the surface of the electrode, basically like a supercapacitor. But it is getting charged as heat goes through, and as that ionic liquid create that voltage difference inside of the cell.
Question from Ashok. Can you comment on the cost of your product when scaled up?
So it's a very interesting question, because one of the main advantages that we have is that because we are a synthesizable material, as we scaled up, the main component of our devices, cost will reduce significantly because we can go to a higher synthesis scale and then have a much higher production rate. So we believe that as we go forward, as we integrate more into market, we can reduce the cost of our devices significantly.
Can you comment on the competitive advantage compared to the organic ranking cycle?
So we are not directly competing with organic Rankine cycle. Organic Rankine cycle is mainly used for high temperature application, which then they have the 23% efficiency. We have 12% efficiencies, but we don't go after that market. We are mainly going after recovering waste heat in a much portable way and much less initial cost to provide power for sensors. But we do believe with reaching our second milestone, we will be able to reach 23% efficiency at high temperature, which then in that case, the difference between us and organic Rankine cycle is that we don't have any moving parts. So our life cycle cost is much less than organic Rankine cycle. Our lifetime is over 20 years, which I bet no organic Rankine cycle can run that long and have no cost.
A follow-up question. What is the efficiency and how does it compare to piezoelectric generators?
So piezoelectric generators are mainly converting the vibration to electricity. We are converting waste heat to electricity. So the conversion is basically then is more solid. Vibration conversion to electricity. Ours is heat conversion to electricity. We don't need any vibration. We're just looking at any type of steam injection, boiler, compressor, which are either they're running at very high temperature or they're in contact with even environment. We just come in between them and then start harvesting the heat waste that they're losing.
Last question from John Jeffers. What is your approximate cost per watt?
We did some studies. It's $100 per watt, and that's not completely accurate. But based on we see that a $500 device can provide around 5 watt power if we have a good heat source, and it's something that it is depend on that. So it depends on the temperature of the heat source and the environment, but it's on average it's around that number.
Can you say that number again?
We are predicting $100 watts, but that kind of comes to play if you have $500 device which provides 5 watt power.
Well, Ali, thank you so much. We're going to go ahead and move on to our next startup.